This is the notes for section 9.1, exponential growth. If you haven't done so already, make sure you pause the video and read the section before continuing on with this video. So first of all, let's take a look at what an exponential function is. We've looked at other functions prior to this chapter. We've looked at quadratic functions, we've looked at linear functions, and we've experienced a few other ones here and there, but not as much formally as those two. So today we're going to begin looking at exponential functions. And when we say a function is exponential, we say it's of the form ab to the x. Okay, and in order for it to be in this form, a cannot be equal to 0, which would make sense because if it's 0, then the whole thing is 0. B has to be a positive value, so it has to be not equal to 0, but greater than 0. And b cannot be equal to 1. So those are some stipulations about a and b in order for it to be an exponential function. Okay. When we do this, we're gonna, if we were to graph this, we've got what we call an exponential curve, and we'll take a look at what that looks like in a little bit. Okay. Now, as you look at the equation y equals ab to the x, with a greater than 0, then b is the growth factor. Okay, so when we say b is the growth factor, it determines basically how fast that function increases. Okay, that number corresponds with the r, that constant ratio in a geometric sequence. And in general, if b is greater than 1, then we have exponential growth. Okay? And in the same equation, a represents the starting value. That's where we start out. That's the value of the function when the variable x is 0. So those are some key components about exponential functions. Now when we talk about an exponential curve, I want to show you a graph of one of those here. And this is from the example that's in your book. But you'll notice in an exponential curve, it's going to intersect the x-axis here, or excuse me, the y-axis. It will never intercept the x-axis, and it will increase relatively quickly, and that the how quickly it increases is dependent upon this number here that is being raised to the power of the independent variable. So that's a general idea of what an exponential curve looks like, and we'll be talking a little bit more about the properties of those throughout this chapter. Next, I'd like to take a look at types of exponential functions. Now, we've actually looked at exponential functions prior to this chapter. It's just that they were always discrete, as opposed to what we're going to be looking at in this chapter, where they're continuous. And we'll talk a little bit more about what the difference is there. We've explored that before. But with the geometric sequence, that would be considered exponential. Okay, it had a independent variable. In those cases, we generally call that n. The dependent variable was g sub n, and remember that's how we write sequences in that sub form, like g sub n's form. The starting value, generally we work with g sub 1, the first term. Sometimes it can be referred to as starting at g sub 0, but we've tended to work with g sub 1 as our starting value. And then there was always a growth factor there as well, and that was r, the ratio between terms. So that was a geometric sequence. Compound interest was also a exponential function. Okay? Generally, once again, we work with it in terms of being discrete, as in the amount of time had to be a specific number of years. So generally we worked with that primarily in a discrete fashion as well. And then finally, we're going to look at exponential functions. And exponential functions, our independent variable is x, our dependent variable is y, kind of like we generally work on with when we were working with linear equations and quadratic equations. But with exponential functions, the starting value now is going to be a, and that value will be the y-intercept. So a is always the y-intercept of that exponential function, and b will always be that growth factor. So let's take a look at example 1 here. It says a certain type of bacteria doubles in population every hour. Suppose an experiment began with 300 of these bacteria. Well, we give you the equation here, but I want you to be able to think about this as well. If it doubles, what doubles tells me is it's telling me how fast it's growing. So that doubles is represented by 2, and that would be my growth rate. The 300 is the amount of bacteria we started with, so that's my starting point, or A. So when we write this equation, 300 times 2 to the t, where t is my independent variable, it would make sense because A is my 300 and B is my doubles, or 2. Okay, so it says use a CAS and the equation where f of t is the number of bacteria after t hours. Estimate the number of bacteria after 3.5 hours. So first thing I'm going to do is I'm going to come over to my calculator and I'm going to define that function. So I'm saying f of t is equal to 300 times 2 to the t. I've defined it, it just says done. Now I want to find out what f of 3.5 is, because I want to know how many are after 3.5 hours. Well, if I do that, I get 3,394.11, and I believe that the question asked us to round our answer. Oh, actually on that one it didn't say to round our answer, so we'll just do it to the nearest bacteria, which would be 3,394. Okay, so that's the value that we're going to put down there, 3,394. And you'll notice that I put approximately there because we know it's not exactly that, but after 3.5 hours, that's about how many bacteria we would have. So let's take a look at part B then. It says estimate to the nearest hundredth of an hour when there would be 10,000 bacteria. Well, to do that, I'm solving this equation. 10,000 is equal to 300 times 2 to the t. I'm letting 10,000 be equal to the value of the function, because remember the value of the function is the number of bacteria. So I'm going to come over to my calculator and I'm just going to solve that equation because I don't have a way to algebraically solve for that yet. So I can say solve this for x, and if I do that I get to the nearest hundredth would be 5.06 for that value. So my t value then would be about 5.06 hours until we hit 10,000 bacteria. Okay, part C then says use a graph to estimate f of -1/2. Now we could plug it in the same way we did 3.5, but we want to kind of take a look at the graph here a little bit. So what I want to do to do that is I'm going to come back over to my calculator to where I have that graphed. So I've got the graph of that plugged in. f1 of x is equal to 300 times 2 to the x. Now to help me figure out where that is, what I'm going to do is I'm going to put a point on my graph. So I'm going to go to Menu, Points and Lines, and select Point On. And I'm just going to click on my graph. And I don't care right now where I put it, just anywhere is fine. And click a point there. And then what I'm going to do to help me figure out where that is I'm going to come back and just got to hit escape now so you're out of this completely and you're into the text. And what I want to do is I want to change the text, this text right here. So instead of this, I have -0.5. Okay, because that's what we want the value of the independent variable to be -0.5. So if I hit enter, it's going to disappear. I don't know where that point is. But what I can do is I can change the window of my graph, or if you want, you can just drag. When you get the hand over the axis like this, you can pull the axis down a little bit until it shrinks in a little bit. And because mine is recording here, it moves very slowly to do this. So I'm going to actually zoom out here. And if I zoom out far enough, you can see that at -0.5, the value of the function is 212. So that would be the value that we would look for there. So when I'm looking for my answer for part C, I would just say f of -1/2 is equal to 212. So let's take a look at example 2 here. It says from 1990 to 2000 the population in California grew by about 1.3% per year. Let C of x equal the California population x years after 2000. In 2000 the population was 33,871,648. Suppose that the growth rate continues. Okay, so we want to write an equation for the population of California to begin with. Well, if this is the year 2000 population, that's where our starting point is, I'm going to let that be my A value. So 33,871,648. That's A. Now my B value would be the growth rate. Well, if I have a 1.3% growth rate, that's 1.3% more than the 100% that I started with. So what that is a growth rate of 1.013. Okay, so it's 1.3% more than 100%. Okay, and then we're going to raise that to the x power, x representing the number of years after 2000. So this would be an equation or a function that we could use for the population of California. Part B says use your formula to predict how long it will take for the population of California to double. So instead of this, so what I really want is I want my C of x to be double this number. So I'm just going to say 2 times 33,871,648. Okay. Now we could figure that out, but I'm just going to put that in my equation like that, is equal to 33,871,648 times 1.013 raised to the x power. Now I want to solve this equation for x. So now I'm going to use my CAS to go about doing that. So in my calculator, this is what I'm going to enter, solve, and then 2 times this number, or which is this number right here, 67,743,296, times my original A value times 1.013 raised to the x value, and I'm going to solve it for x, so I have to put comma x after it. If I do that, I get 53.6648, which means that x is approximately equal to 53.7 years. So that's about how long it will take for the population of California to double. And then part C says predict how long it will take for it to double again. Well, in essence, that's 4 times my original amount times 1.013 raised to the x power. Okay, so I'm going to solve that the same way I solved the last one. So when I do that, I'm going to enter solve, and I just put in 4 times my original amount. Okay, now you'll notice that I get x equals 107.33, but I have to subtract the original amount of time that it took for it to double to find out how much it doubles again. So if it was 53.7, we've got 107.3, so roughly 53.6 roughly 53.6 years. Okay, so if I do that subtraction there, we get about 53.6 years for part C.